So, in the previous session we looked at the origin of stress induced birefringence. We set up basic framework for describing the effect of polarized light passing through birefringent material or a stress induced birefringent material. We discussed the stress optic law, and I also showed you that the principal stress difference and the orientation of the principal stress directions are the main quantities that are picked up by light that is passing through a photoelastic object, right, a stressed photoelastic object. So, if I just go back to where we ended in the last session, we have this formulation of the problem which we introduced. So, you have a light source excuse me, on the left, you can see here, and the light source is passed through a polarizer sheet which has a polarization axis, we call that P, and the light that is coming out from this polarizer sheet then passes through the actual loaded object. And remember, we assume that the object is 2 dimensional, the stress state at least is 2 dimensional. The object itself could be thick, but if the stresses are planar for now, then our assumption will work, and all the stuff that we have derived will be applicable. And once the light, polarized light passes through this, of course, because the optical axis is oriented in the direction of principal stress, one of the principal stresses, the refractive index in that direction is different from the refractive index in a perpendicular direction. So, the two waves essentially split, the two polarizations split, and they travel at different speeds, and then they recombine once the light exits the material, and then there is some phase lag delta. And we basically probe this phase lag by using another polarizer which we call the analyzer, or A, that is placed perpendicular to the initial sheet. Okay. So, remember that if there is no stress, or if the material is not birefringent at all, then you will not see anything. This will only allow polarized light in this direction, the electric field vector is like this, and this will only allow field vector like this, right. And since they are perpendicular, if you did not have any stress field at all whatsoever, then you will completely get a black image, right. So, this is referred to commonly as a dark field. We will talk about this in more detail today, and this is what you are going to pick up, right. And then we said that there is a systematic way of looking at this stuff. So, your approximated or the equivalent way of looking at this is you have one vector like this, E1, this is our polarization direction, and we represent the entry point of the object with these two axes, we represent the exit point with these two axes, and the distance through the object, the thickness of the object is h. The light going through first has these two directions, E2 and E3, one is a higher refractive index direction compared to the other, and they are inclined at some angle theta, right. These are also the principal stress directions like we discussed from the stress optic law. So, this depending on the orientation theta, you will have different orientation of the principal stress, and the light that is coming out finally will have a delta, and we said that you can calculate the delta by systematically taking components of the incoming light along these two axes, getting one ahead of the other by delta. So, one goes ahead by delta by 2 and one goes behind by delta by 2. So, the net change is delta, and if you do that and then you recombine at the end, the analyzer being perpendicular to the incident polarizer is going to basically give you the x component of the final field, and that we determined from here, and we saw that it is going to be something that looks like a combination of trigonometric terms. It has this E naught sin 2 theta sin omega t sin delta by 2 type of thing. And then we also briefly discussed this notion that the frequency of the oscillation of the electric field of course is extremely high. For example, if you take the lower frequency components or the larger frequency components, which is red light, typically you are looking at something that is the order of 10 power 14 hertz, which is extremely high, and there is really no such scheme that you would use in any normal camera to pick up these types of frequencies, and so the time scale of observation typically averages out these oscillations, and that is what you actually end up observing, right. And so we said the intensity is proportional to the square of the field. That is a well known relation in optics or in electromagnetism, and excuse me, since the I is proportional to E square, we only need to look at the average value of I, that is what we discussed, time averaged over periods, and this will give you a constant does not matter what the exact value of the constant is, but it will give you a constant, and the final intensity you observe is just functionally at least dependent on these two factors. And we said that you can get a 0 intensity if either sin 2 theta is 0 or if sin delta by 2 is 0, right, and those gave us the two conditions. One corresponds of course to what are called isoclinics. I mentioned that clinic refers to inclination of course, and these give you loci of theta equal to m pi by 2, and the others are called the isochromatics, and these correspond of course to delta being 2 m pi. Okay. And notice also that the delta, as we mentioned, depends on the wavelength. So, typically if you use white light, the isochromatics are, you can see them as colored fringes, and the isoclinics are always black, right, because they depend on wavelength. Right. Okay. So, now let us continue from here, and let us go about this business of actually identifying fringes and calculating the stress tensor. Okay, that is ultimately that is our aim, that is what we want to be able to do. And so this is the first step. Now there are a few pieces of terminology that I will include here, just so that if you looked at a book on photoelasticity, you will be able to see, you will be able to relate to some of the terms that are commonly used there. The first is this idea about using the polarizer and the analyzer. Remember, both of them are just polarizer sheets. If you use them in the form that we discussed, I mentioned at the start of today's session that this is called a dark field image. What you see here at the end is a dark field image, and a dark field of course is because in the absence of any stresses, in the absence of any birefringence, you will get a black image, right, that is a dark field. You can do the analogous thing where the polarizer and the analyzer are actually parallel to each other, and in this case the default image changes. So, if you do not have stresses now, whatever is emitted, pass, or whatever rather is coming through the polarizer, is transmitted through the polarizer, is picked up by the analyzer, and this is called a light field or a bright field image. And you can use either one, right. There are advantages to one over the other, we will discuss them a little later today. Okay. The other piece of nomenclature is that this is usually called a linear polariscope, and linear because you have only a linearly polarized light coming through the object, and you are looking at the other end and seeing what is there either in a dark field or a bright field image, right. There is also something called a circular polariscope, and this uses circularly polarized light, right, as opposed to linearly polarized light, and you can just use a very simple trick to convert linearly polarized light into circularly polarized light, and the trick is basically to use something called a retarder plate. We will discuss the terminology, but the distinction between these two is important, right, to remember. The main advantage of using a circular polariscope, as we will hopefully show today, is that with this you do not get any isoclinics. So, you can eliminate isoclinics completely with a circular polariscope, and you will only get isochromatics. Okay, just by sheer cleverness of its construction, it gets rid of isoclinics. Okay. So, just the reason this is important, of course, if you just look at a white field white light based image, you can clearly distinguish between the two, right. You can distinguish an isoclinic from an isochromatic because one is colorful, the other one is black. But if you use monochromatic light, so if you have a single wavelength, then both will appear black, right. So, if you have a single lambda, both are typically dark. So, then you need to know how to distinguish between the two, and the circular polariscope allows you to do that because the isoclinics do not show up. That is why it is useful. Okay. Okay. Now, there are a couple of other optical elements that we need to know about. The first is what is called a quarter wave plate. Okay. And as the name suggests, this basically results in delta of pi by 2. So, that is a quarter wave, delta equals 2 pi is a full wave, delta equals pi is a half wave, delta equals pi by 2 is a quarter wave. And it is basically just a birefringent plate we will represent it like this. Okay, it does not matter how you represent it as long as you know what it does, and it has a certain thickness h or h naught, let us say, and it has a certain optical axis direction. So, this is let us say the optical axis, and this is perpendicular to optical axis, and you can take this and orient it any which way you want from your light source. Let us say you have a polarizer first, you can put this plate at any direction like this or whatever, right. So, your direction with respect to let us say the y axis is theta. Okay. So, this orientation and it retards by delta equals pi by 2. Okay, that is what a quarter wave plate does. A half wave plate is analogous, you can take delta equal to pi, and that is what a half wave plate will do, and I am not going to draw it for obvious reasons. Okay. But the fact is that the retardation depends on the angle, right. So, the two waves that are retarded are actually at an angle, the relative refractive indices are at an angle to the incident wavelength, so incident polarization, and that is important to remember. Okay. So, how do we eliminate isoclinics? Okay, I told you that a circular polarizer gets rid of isoclinics, and how do we do this? It is a very simple, well, in hindsight very simple construction. Let us go back to our z axis like we did last week in the last session. You have your polarizer here, you now put, let me use a different color for this, you put a quarter wave plate. So, this is the fast axis, let us say, or the optical axis, and this is slow axis. One is optical axis, one is perpendicular, it does not matter, and it is not placed at some arbitrary angle, but it is placed at pi by 4 degrees to the polarization direction. Okay. This of course is perpendicular, but one of the axes, maybe the optical axis for instance, is placed at 45 degrees to the incoming polarization direction. Okay. If you do this and then you let the light pass through your sample, let us say sample is loaded, and then you take another quarter wave plate and place it now cross to the original quarter wave plate. So, now you have your slow axis here and the fast axis here. So, if the optical axis let us say is denoted f, optical axis of the quarter wave plate is f, then the second quarter wave plate is kept perpendicular, the optical axis of the second quarter wave plate is kept perpendicular to the first one. Okay. And then you put your analyzer as usual at the end, right, then you are observing from here. So, you can actually show, and we will show that in a minute, that the intensity now is purely just sin square delta by 2. There is no sin square 2 theta term that was there before, this is independent of theta. So, you only get intensity goes to 0. This is of course the averaged intensity. When I say intensity, omega is averaged out, we will take that for granted now. The intensity goes to 0 only if delta is 2 m pi as usual, right. So, only isochromatics. Okay. So, I will make a small note about this light field dark field business. Before we move further. The remember dark field was what we first discussed. You have this and you have stuff in between, which I am not going to draw. The if you do not have anything in between, let us say, then we mentioned that the image will be black. So, you are actually picking up components that are exactly in phase with P, right. Here if your eye is here, if all the components are exactly in phase with P, then A will cut it off and you get a dark field, correct. So, if the phase difference is some multiple of the some multiple of the phase of the incoming wave, then the A is going to cut it off because it is perpendicular to P, right. So, if you will get a dark band if you have stuff that is an integer multiple of the phase of P, right. So, difference is integer number of 2 pi. So, usually people define something called the fringe order, again you will see this term used quite often. It is defined as delta by 2 pi. Okay, so, in the dark field, so this is the dark field image, you will always pick up integer fringe orders. Okay, n equal to 0, okay, 0 is trivial, 1, 2, 3, 4 and so on, right. Anytime you pick up a band a dark, this corresponds to dark band. So, anytime you have a dark band in the dark field image, that corresponds to a integer fringe order, delta is 2 n pi. Now, the exact opposite happens when you have a bright field. So, if you have A here, you are looking at it like this. In the light field case or the bright field case, the A is allowing stuff that is in phase with P, the A is cutting out stuff that is perfectly out of phase with P, right. So, now delta by 2 pi is half integer or a fraction, right, for a dark band. So, ideally if everything is in phase, A will allow everything in phase. So, you will see a white or a bright image, but if it is out of phase, exactly out of phase, which means it is pi, 3 pi, 5 pi etc. out of phase, then you will see a dark band. And so, that delta by 2 pi, the n that we have here corresponds to a fraction, it is called a fractional fringe order. People will refer to this as fractional fringe order. Okay, so, you will get n equal to half, 3 by 2, 5 by 2 etc. Okay, and here you have n equal to 0, 1, 2 and so on. Okay. Please keep this in mind because it will be handy when we discuss this idea of compensator a little later on. Okay. Good. So, it is a little bit tedious if you remember what we did little while ago, the end of the last session. We had this light source and we had 1, 2 vectors here, we had 2 vectors here and we had 1 vector here. So, we call this E1, E2 E3, E4, E5 and E6, right, and then we took components of E1 along E2 and E3, and then we took E2 and E3 along E3 and E4, E4 and E5, and then we took that along E6 and so on. So, this entire trigonometry is actually very simple. It can be simplified using what are called transformation matrices, because you are finally just doing a rotation, right, and a retardation. Those are the only two things you do, and it turns out there is a very simple way to do this using transformation matrices. This methodology is often called the Jones matrix or Jones calculus method, although like I probably mentioned before, this has nothing to do with calculus. So, Jones matrix is probably a better term to use. And so, we represent each optical element by a matrix. Okay. So, for example, if let us say the light coming from the source has some arbitrary orientation of its polarization, right, E0 bar, then what P will do or a polarizer will do if it is kept along the y axis, it will basically correspond to a matrix that looks like this. Okay, I will explain this notation in a minute. So, you are assuming that your incoming electric field vector is of this form. So, E0 bar is E0 x times I hat plus E0 y times j hat, naturally because it has to be in the xy plane. It has two arbitrary components and it has this oscillatory thingy going along with it, e power I omega t. Then the polarizer basically picks out the y component. So, if you refer to this as representing P, then what P does to the light wave is it does this matrix times the incoming wave, and if you do this matrix times the incoming wave, you will get 0 into this will plus 0 into this will give you 0, 0 into this will give you 1, right, times E0y. So, after the polarizer the light looks like this, right. So, this is after P. Which is what we have, right. So, you can associate a matrix with each of these elements and you can make them do stuff to the incoming wave and transform it into some other wave that is going out. That is the basic idea, right. So, now the question is, okay, you have let us say this fellow that is rotated at some angle theta. Remember this, we had to resolve the E1 along E2 and E3 using cos theta, sin theta and so on. How do you do that? So, the way in which you do this is you take for let us say for rotation, you take the incoming vector, let us call it V bar, okay, whatever, just a general vector, and you transform it, rotate it, right. So, what does a general retarder do? What does a general birefringent material do? It rotates to a direction along theta E2 and E3, it retards it. So, it does something else, we will call that T maybe, and then the final components are back with respect to the original coordinate system. So, you have an R transpose or an R inverse. Okay, so, this is your rotation matrix. And this is the inverse rotation matrix. Since the matrix rotation matrix is orthogonal, the inverse is equal to the transpose, right. Okay, so let us look at this, let us look at what this guy does. So, M is R transpose T, maybe I should use a different, okay, that is fine, I will just refer to this as R inverse, that is the same thing, right. I want to avoid the use of two T's, R inverse T R, okay. This I am claiming represents what is going on here, right. and you can already see that I have not told you what T is, we will do that in a minute. You can already see that it is sort of intuitive, which is incoming wave is coming in, you rotate it and refer to it in two different, in a different pair of coordinate, different pair of basis vectors, which is now E2 and E3. So you get its components along E2 and E3, then you retard it somehow by applying this matrix T, and then you rotate it back, right, because you are again looking for components E1 and E2 along the x and y direction, that is your original axis, and so you take it, retard it, rotate it, retard it, rotate it back, right, that is what you do, okay, and that is basically what this is doing. So if you look at this T is basically this, okay. Why is that? Because what did T do at the start? If you remember, the E cos omega t became cos omega t minus delta by 2 and 1 became cos of omega t plus delta by 2, right, that is what this guy does, that is what T does, and this is a very compact way of representing the same thing. The only caveat now is that you have now got an imaginary component, so you have a real part and an imaginary part, and at the end of this entire transformation you do all the stuff, at the end of everything you take the real part, okay, that is the understanding we have. Because anyway finally what you are going to measure is the intensity is proportional to the square is the complex number times this complex conjugate, which is real anyway, right. So this complex stuff will go away as we will see, okay. So let me write down this general form for M. Remember the rotation matrix, maybe we will start with let us start with the rotation matrix. So the rotation matrix is cos theta sin theta minus sin theta and cos theta. The retardation matrix which we just defined is this, and the R inverse of course is just the transpose of this, and the signs will exchange signs, feel part of the pun here, okay. So this is the rotate by theta, retard, rotate back by theta. So if M is R inverse T and R, then you have cos theta sin theta minus sin theta and cos theta, you have e to the power of minus I delta by 2 0 0 e power I delta by 2, and you have cos theta, sorry this should be inverse, right, so it will be negative, sin theta minus sin theta and cos theta. And if you open this out and take the real part, imaginary part, e power I delta by 2 of course is cos delta by 2 plus I sin delta by 2. If you use that and you do a little bit of algebra on a good sunny day, then you will get something that looks like this. The exact form is your plus minus signs are not that critical at this point, but where the sines and cosines go are obviously critical. And you have a complex conjugate of the first term. This is what M looks like, okay. So a general optical element will do this, right. If you have a body whose principal stresses are in this direction, it will do exactly this. If you have a quarter wave plate whose orientation is in some random theta direction, it will do this with delta equal to pi by 2 and so on, right. Any optical element will do the same thing. So this is a general transformation for any retarding optical element, right. And for a polarizer you have delta equal to 0, and for because there is no retardation it is only going to pick up a direction, you have that matrix that we wrote before. So you have 0 0 0 1 like I showed you before. For a quarter wave plate quarter wave plate at pi by 4 to the incident direction, or let us say to the y axis pi by 4 to the p bar direction or y axis that we had in the circular polariscope that I had introduced before, the M is basically going to look like this. As an example, right. So, here I have taken theta equal to 3 pi by 4, but you can construct any optical element like this. Okay. So, now we will just quickly, before we conclude today, we will just quickly look at an example of a plane polariscope and see what this guy looks like. So, remember this is just your light like this, P like this, your object which is here loaded, and A like this, right. Let us look at the dark field for instance, right. So, let us say your incident light is coming in after this. So, this is EI y, this is my x and this is y, EI y j hat, that is your incident light, and your final light that you are going to get, the exit light, of course because the analyzer is now along the x, you are going to look at only the x, but okay, let us in general this will be M times EI bar, M being the matrix we wrote down before, right. And so, if in general your E0 has components E0 x, E0 y, it is going to be matrix M times EI x, which is 0. So, I will get rid of this, and EI y, right. That is the incident light direction. Okay. And if you go back and put that matrix, remember what the matrix was, we had cos delta by 2 minus I sin delta by 2 cos 2 theta cos delta by 2 plus I sin minus I sin delta by 2 sin 2 theta and minus I sin delta by 2 sin 2 theta here. If you acted this, so M times 0 and E I y will basically give you this times this plus this times this, right. That is the first term. So, you will get a minus I sin delta by 2 sin 2 theta, and then this times this plus this times this. So, you will get cos delta by 2 plus I sin delta by 2 cos 2 theta. The whole thing, of course, I am just taking the E y, the value E y out, the e power I omega t. Okay, simple matrix algebra, nothing very complicated going on. So, this is your out vector, and if your analyzer is set such that you are looking at a dark field image, then you are basically going to measure an intensity that is proportional to E0 x times E0 x bar. This is the complex conjugate. So, it is the magnitude of that vector, of course the complex vector, vector's magnitude, and the fact that you are cutting out the y component because the analyzer is horizontal along the x means that you are only going to look at this component, and if you take a complex conjugate of that, you will get sin square delta by 2 sin square 2 theta with some stuff that is going on, and the averaging stuff and so on applies as we did before, right. You will get e power I omega t minus I omega t, does not matter, okay. And this is the same as before, right. You have again your isoclinics and isochromatics and so on. Okay, so this matrix approach works very well. It is a very simple method to use. It just makes life easier, keeps track of what is going on where. So, what we will do in the next session now is we will use this framework to look at a circular polariscope, okay. And the moment you do that, you will realize that it is very simple to write down an expression for the final intensity, and you will see that the theta does not appear. So, the claim I made earlier about isoclinics going away will be clear, and then we will see how you can use this in a more general framework and how you can interpret the principal stress orientation directions, principal stress magnitudes and so on from that.